Hello and welcome. Today, we're going to explore the fascinating world of black holes through the lens of signal processing. We'll be using MATLAB to analyze real and simulated data to understand gravitational waves and Doppler shifts in black hole systems. Black holes are among the most extreme objects in our universe, regions of space-time where gravity is so strong that nothing, not even light, can escape. We'll be focusing on stellar mass black holes, which form from collapsed stars and often exist in binary systems. Studying these objects helps us understand fundamental physics and the evolution of our universe. In 2015, LIGO made history by directly detecting gravitational waves for the first time, ripples in space-time predicted by Einstein. A century earlier, these waves are produced by cataclysmic events like black hole mergers, creating characteristic chirp signals that we can detect and analyze. When black holes orbit in binary systems, they cause periodic Doppler shifts in the spectral lines we observe. By measuring these shifts, we can determine orbital parameters and even calculate the masses of these invisible objects, using what's called the mass function. Our MATLAB project tackles both gravitational wave analysis and Doppler shift measurements. We've developed code that can download real data when available, or generate accurate simulations based on published parameters. Let's look at some of our key findings. Here we see the gravitational wave signal before and after processing. We apply bandpass filtering to isolate the relevant frequencies, use wavelet transforms to reduce noise, and employ Hilbert transforms for envelope detection. These techniques help us extract the clean signal from noisy data. On the left, we identify specific spectral lines and measure their Doppler shifts. On the right, we see how these shifts create a radial velocity curve over time. From this periodic pattern, we can determine the orbital period and calculate the mass function, which gives us information about the black hole's mass. In our simulation, we measured a velocity semi-amplitude of 75.2 km per second. We also investigated how sampling rates and quantization affect our ability to detect these signals. Lower sampling rates can miss important details, while coarse quantization introduces errors. We use cross-correlation to find relationships between different signals, and Bayesian methods to estimate parameters with uncertainty bounds. Our analysis of the simulated black hole binary system revealed an orbital period of approximately 25 days, a mass function suggesting a black hole of about 10 solar masses, and a velocity semi-amplitude of 75.2 km per second. We also quantified how different quantization levels affect measurement accuracy. This work isn't just academic, it has real applications in the emerging field of gravitational wave astronomy. By studying black hole populations, we can understand how they form and evolve. These observations also provide stringent tests of general relativity. Future observatories like LISA will open even more possibilities for discovery. Processing these signals presents unique challenges. Gravitational wave detectors operate in extremely noisy environments. The signals are incredibly weak, waveform models are complex, and the computational requirements are substantial. Advanced signal processing techniques are essential to overcome these challenges. In conclusion, we've seen how advanced signal processing techniques allow us to extract fascinating information about black holes from both gravitational waves and Doppler shifts. This work highlights the growing importance of signal processing in modern astronomy. Future directions could include real-time processing pipelines, machine learning approaches for signal classification, and multi-messenger astronomy combining different types of observations. Thank you for your attention. I'd be happy to answer any questions about black hole signal processing or our MATLAB implementation. You can find the complete code and references on our GitHub repository. Let's continue exploring the universe together.